Swayam Prabha. Digital India. Educated India.
Okay, so yeah, welcome everyone. So this is the second day for this GAN course on materials informatics. So yesterday we delved a lot on materials part of it. So Kamal talked a lot about how you can represent materials, right? How do you generate properties for these materials? He talked about different density functional theory calculations. He also led you through some of the codes by which you can actually generate your data, right? So a lot of things on the material sides were discussed yesterday. And today what I want to do is focus more on the informatics side. So start talking about what is machine learning, a very gentle introduction to machine learning, especially in the context of material science. Okay. So this is what I want to focus in the today's session. Okay. So we'll take a very gentle introduction to it. First, we'll cover one or two cases which are outside of the materials domain. We'll get a feel from those examples, and then we'll slowly bring in the material side. Okay. Very quickly, these are the three main points that you will see from these slides. Basically, we'll be developing a model which is based on some data. We will be using this model to make predictions for new scenarios. And then finally, what we'll see is there is a way by which we can continuously improve this model. Okay, so overall, that's the whole thing about. Okay, so very simple example, ChatGPT. I hope every one of you have heard about it. Okay, anyone who has used ChatGPT? Okay, everyone is using it. Okay, good ways, bad ways, in all ways we are using it. So you're using it meaning you are trusting the model, right? You're trusting it predictions. So now you're trusting something, then you should understand also, right? Why is it working? So any ideas on how is it working? How does ChatGPT work? How is it able to answer your queries? So I know some of you are familiar with these slides. I'll ask you to let others take a dig at it. So what do you think? How ChatGPT is answering your questions? Okay, yeah. It has been trained on some data or all the data actually. But okay, what type of data it has been trained on? All types of textual data. Any example? Yeah, Wikipedia is a very good example, right? So a lot of thing of ChatGPT actually is from Wikipedia, and then books is also right, although that has copyright issues, and there are some legal cases also ongoing in that regard. But books is also another thing. What else? Website links. So website link as such is not, if I give you a Google Drive link, right, that doesn't have much meaning. What you will see is some rubbish letters in it which we cannot make sense of. But what we are looking for is textual data that makes sense to humans. Okay, so all open source data is actually being used, and in fact this data is so large that no one is caring what type of data is being used for the training of these ChatGPT models as well. Okay, so all types of data has been dumped in, and people are using it to build the model. Okay, so that's where some issues are also coming in, because we don't know whether it is right, it is legally right to use everything that has been dumped in there. So all social media data, right, that is open source, you can, that's public domain. There is also data about legal cases. So much of the US government, a lot of democratic countries, right? US government, Indian government, you can actually look at the proceedings of the court. Okay, that documentation is available. So all of that data is also being used. So this is about, there is some model on which it has been trained on this data. So now let's talk about how it is giving you answers. Okay, this model was shown all of this Wikipedia data, books data, but then how is it able to generate an itinerary for me if I want to go for vacation in, say, Jaipur, right? You can write in ChatGPT, I want to go for Jaipur, plan a 3-day and 2-night trip. It will generate that for me. So how do you think it is doing it? Okay, so you use a lot of jargons there, which is okay. So when I enter that plan a itinerary for Jaipur, so what she is saying is that words that I'm giving, it is taking that and then associated with it. Okay, so a lot of leaps here. It is taking that data in and then predicting or generating something. Fine, but how is it doing it? That's the whole question, right? Sorry? Vectorized text. So what do you mean by that, vectorized text? You are right, but what is vectorized? Yeah. So these are all types of machine learning models, but I just want to go to a little bit more detail. What do they mean? Like what is their essence? Hmm. Yeah, so you are saying everything right, but I am looking for a more simpler explanation of what is happening. Yeah. Yeah, so that's a very good important point, which is it is predicting word by word. Okay, so it is not something that it takes the query that I have given and then searches in the database and then gives me an output. This is something what a Google search is sort of doing, right? It gives you that these are the full outputs. But this is something different. This is a generation process where the generation is happening word by word. And someone said it correctly. It is prediction made word by word, wherein what you do is you take in the last, say, whatever is the user input so far. So your query, so that prompt that you give, what you type in the browser, in your ChatGPT browser, that prompt is basically a query. That query is the input to the model, and from that comes the first word, which is the output from the model, and that output is nothing but a probability that this particular word will occur from the entire dictionary of words that is possible. Okay, so basically the model is just learning a probability of next word. So imagine there is a whole dictionary of words that is possible, say 10,000, 40,000 words are possible in the entire English dictionary, and you are making a prediction that out of those 40,000 words, which is the best, which is the most probable word that is should be predicted given your query. So once the first word is predicted, your entire query plus the first word that was predicted is now the input. Then the second word will come. Your entire query plus the 2 words that have been predicted gives the next word. Okay, so this way the model is in essence nothing about but just predicting the probability of the next word given these previous set of words. And by training the model on this entire huge internet data set, it is able to come up with some decent outputs which are useful for us. Okay. So there are a few approximations. I mean, I simplified a few things. Instead of words, there is something called tokens. Okay. Instead of just looking at the most maximum probable word, we look at something else. Okay. So there are a few details here and there, but this is how generally this thing is working. And then how probabilities are computed and everything, that's where the embeddings and the vectorization will come into picture. Okay. So, but one thing you can do is you can obviously ask ChatGPT to answer it for you, how it is working, or go to OpenAI whose GPT model is there, and through that you can get to know. But what is the important thing, again, I want you to get from this example, there is a past data which is our internet open source data set, and it is predicting. Okay. The features thing is the vectorization we slightly touched upon, but it's a little bit difficult to understand what I mean by features in this case. Any model will come down to past data, it making a prediction, and the predictions will be made using this features thing. Okay. So let's take one more example. This will be slightly from a different domain, which is say someone approaches a bank for getting a credit card or for some loan. They approach the bank, and then the bank will basically give you a form that, okay, please enter your data. That will allow us to judge how much loan amount should we approve for you, how much credit limit you can have, things like that. Okay. So now the bank needs to decide. So say you are a bank and you need to decide how much credit amount I should approve for this person. So how can the bank decide? Because what banks want to do is they want to minimize their minimize the risk that the person who is coming will be a defaulter. Okay. So how can they do it? Go back to this example of past data, credit history. Okay, so you can look at the credit history of the person. Okay, so credit history will be something like credit score is something which is sort of part of this form. Okay, along with your because you can also check it, right? Credit score, you can check it. So you can, so everything we are talking about is sort of part of this form. The user can input. What else can the bank do? Transactions, again, something related to monthly salary, how much savings you have, right? So basically bank needs to decide on what, whether the person is working or not, how long they have been working, what is their salary, okay, what is their savings, do they, what, how much amount of liquidity is there, things like that. Okay. What else? This entire thing is about this person. Okay. Is there any other data that the bank has, which is, yes, yeah, correct. So the bank not only has this data set, the bank also has data set about all the previous people it has given loan or credit card to, right? For all those people, it also knows the same form these people would have also submitted. Okay. So wherever you see dot dot here, this thing is something that is known to the bank. Okay. So all previous N people, the bank knows their age, their salary, everything. What they also know is this Y column. This is very important column. This is the column which is where they also know how much credit loan amount we approved for it or how much credit limit we put for this person. So this thing is also known to them. And basically the question is, if a new person come, N+1, for which I know the details, can you tell me how much is a good credit amount for this person? So what bank can do is simply look at its previous history of good creditors, and they already know this Y value for them. They already know how much was a good loan amount to be approved for them. Given this, now can I make this prediction? So this is now the problem has converted into. So what the bank can do is, the bank will simply try to learn a function f. Okay, this function f will take input as the features of the people, the previous people who have approached the bank, and it will try and output whatever the correct loan amount that these people were given, the good credit amount that these people were given. Okay, so basically there is a mapping between your x's versus the y. Okay, so that function is what the bank will try to learn, and this function is nothing but your model. Okay, this is your model, this is your hypothesis, your machine learning model. The input to the function is nothing but the previous, this is the history or the form of that person. In other words, these are also the features or the attributes of that person, and output is basically the prediction. Okay, an estimate about the good amount that can be given as loan. Okay, so this is how the bank can actually solve this problem. So now we'll look at this problem again, but now from a material standpoint. Okay, believe it or not, that same problem we can do it for materials. Just like the bank had history of good creditors, we have data of materials. Okay, we have different materials, whether good materials or bad materials depends on their value. So I am looking for high band gap materials, then I am looking for those those materials for which the band gap value is larger, say 6 EV, 7 EV, so on. Okay, it can be also about, say you are in the domain of alloys, then generally we are looking at hardness, yield strength, things like this. So these could be different alloy compositions and the associated strength values or hardness values. In the domain of polymers, this will be different polymers and the associated glass transition temperature, okay, or their polymer dispersity index, things like that. So properties associated with different polymers. And what we want to ask is, if I have a new alloy, can I predict its hardness? If I have new polymer, can I get its glass transition temperature? Something similar to, if I have a new creditor approaching me, can I predict what will be a good loan amount? Okay, same thing. Now for the bank case, I know how to give attributes to my person, right? We talked about their age, their salary, saving account, the savings and so on. Similarly, I need to somehow make a judgment about the materials features, materials attributes. Okay, so this is how we'll do next. This is actually how it is done. So you take these materials, your alloys, your polymers, ceramics, whatever it is, you do something called as fingerprinting. So fingerprinting is nothing, you just represent each material in form of a vector. Okay, all the x's that you see here are some numbers. Okay, and because it's a sequence of numbers is called a vector, right? If you're talking about a three-dimensional vector, generally we are used to x, y, z coordinate. Okay, so but now in this case I am calling it as a m-dimensional vector. The dimensions could be m. M could be of the order of 10, 20, 1000. Yesterday when you were talking about Jarvis, we were touching 1500, 3000 of that order, right? So m can be very large. Okay, but the important point being that all this vector cumulatively represent your material. These are attributes of your material. And once you have this fingerprint, you basically again do the same thing like the bank problem. Basically you map your fingerprint to the property value. So slides are a little bit formatting issues here. So this arrow is pointing to P1, this arrow is pointing to P2. Okay, and the reason you can map them is because these properties are known to you. This is a known data set, right? Just like the bank knew that these are good creditors. Okay, And once you map them, mapping them basically means you learn a function. That function will take as input as the attributes of the material, and it will output an estimate of the property of that material. Okay. So coming back to the problem that we wanted to solve, given a new alloy, can I predict its hardness? What will we do? Once we have done this on the historical data, once I have learned my function on the historical data, I will take this new alloy, I will go through the fingerprinting step, I will represent it as a vector. The same vector I will give as an input to this function, and the output will be an estimate of the hardness of that alloy. Okay. So this is how you will be able to make predictions for new materials. Okay. So this function f again is nothing but your machine learning model. The input to the function is the features of the material that are features or fingerprint, and the output is an estimate property that you had learned based on the database that you have. So when this was an alloy and a hardness database, your output is an estimate of the hardness. When this is about polymers and glass transition temperature, then this output is about an estimate of a glass transition temperature. Okay. So why is this thing very useful? I mean, machine learning, a little bit hype is there, a little bit of excitement is also, I mean, lot of excitement is also there. But what is the major reason? What is it that machine learning is able to do that the previous methods were not able to do? So what do you guys think? Yeah, so even DFT can do that. I can run MD simulations and also make predictions about the property. So all the physical models, generally speaking, all the physical models, if we want to get reliable information from them so that we can guide our experiments, they are very slow. They are very computationally expensive. Okay. Whether you talk about weather model, the weather climate model, or whether you talk about just simulating, say, melting, simulating glass transition temperature. Can you run a DFT calculation to simulate glass transition temperature of polymers? No. In the current age, until we have quantum computers, I guess, we won't be able to do it. Okay. So the good thing about this, I mean, this is the main point why machine learning has become important. It is because first thing, we have good data sets. Material science a little bit behind in the quality of data sets, but still we have reasonable good quality of data sets. Second and more important thing, this whole process of making a prediction from the function is very quick. It is so quick that you can talk about screening thousands, millions, or even billions of possibilities in 1 or 2 days. Okay, if not 1 or 2, maybe in a week. There are people working here on DFT calculations. They are talking about running DFT calculations for 2 months, 3 months for one system. Okay, so this is the order of magnitude difference between how quickly computations can be done using the machine learning approaches versus that of your physics based approaches. Okay, and because this thing is so quick, you can apply it for thousands or millions of cases and then screen out few of those cases which have really the property that you are looking for. So always in some experiments, say you are in catalysis, you are looking for low activation barriers, right? If you are in energy space, then you are looking for high lithium ion conductivity. Okay, so there are always some properties or a set of properties that we are looking for, and what you can do is you can scan your model to thousands of materials and then select those whose predictions are matching with what properties you are interested in. Okay, that's one of the major reasons why machine learning approaches are useful. One more point here, this thing of fingerprint, there are different names to it. Some people call different depending on the community. Some will call it features, some will call it descriptors, some will call it fingerprints. There are 1 or 2 more names which I'm missing right now, attributes, right? So everything means this numerical representation, that vectorization. Any questions here? Yeah. Yeah, so for example, your materials can be textual. So say I am writing alloy, aluminum nickel or nickel titanium. So that is NiTi, right? So nickel titanium at this level, it is textual, which we understand. But at this level, somehow I need to convert my nickel titanium into something which is a number, because all my statistical models will only take input as numbers. Okay. Something has to be done. People will creatively do a lot of things to make it a number, but ultimately this thing will be a number. Okay, so in the next session, we'll actually cover this point in more detail. So please remember, I'll ask for an exercise. Let's see if you remember this. Okay. Okay, so what I talked about so far is only supervised learning. Okay, so this is only one type of machine learning called supervised learning. There is actually three types of machine learning methods: supervised learning, unsupervised learning, and reinforcement learning. Okay. Supervised learning is where labels are provided. So what do we mean by labels? Wherein my property, which is an output estimate that I want, that is a label. In the bank example, the credit amount was the label. Okay, so it is about I want my model to predict the label. So that is how the supervised learning works. In this particular scenario, the input is that feature, which is something having 6 sides. Okay, so that is the feature, and output label is a cube. Okay, so I am asking the model to predict this robot, to predict that it's a cube. Okay. The unsupervised learning, the same scenario, it will be just about grouping the data, clustering the data into different groups without assigning any label to it. Okay, so for example, in this case, what is done is this is one group which is your cubes, and this is another group which is something like your cones, or how should cups. Okay, so these are two different groups without giving any label. The model is not saying these are cubes. Okay, label is not given. It's just saying this is one group, this is group 1, this is group 2, without giving any name to it. Okay, so this is unsupervised learning. Unsupervised learning is also important because the data that we have is usually available without labels. For example, I know a lot of possible alloys. I don't know whether they will have good hardness or not. I do not know their label, but I know these alloys will exist. Okay, so just grouping alloys differently is an unsupervised learning problem, without saying whether this group will have better properties or that will group have better properties, but just distinguishing them itself is a unsupervised learning problem. And then there is the third case, which is your reinforcement learning. So this one is actually is considered to be even better than the other two types of machine learning. Okay, let's see. Does anyone know what does the word reinforcement means?
You give a bonus if it does properly, or you give a penalty.
So basically you give a reward if people do good. Okay, you give them good grades if student does well, and you give them punishment, okay, if they don't do well. So that's how we humans learn. For a kid, it would be something like kids try to explore, play with the environment around them. I mean, they'll do all sort of things. Like they will simply just run and bump their head into the wall just to see what happens. Okay. And then they learn that if they hit the wall with their head, it hurts them. So that is the punishment that the environment is giving. Okay. The parent is not doing anything. Nowadays, parents are not supposed to tell them anything. Okay. You let them explore the environment. When they get hurt, they learn that it hurts me, so I should not be doing it next time. and when they eat lots of chips or chocolates, they get reward. Okay, so they want to do that more often. Okay, so this actually come from psychology. So reinforcement that word and this concepts are very, very old. I think 1940s, 1950s. So Pavlov's dog, that's a famous example. So please check out, just write down Pavlov's dog and check out this thing. So you can actually make a dog salivate just by ringing a bell. You don't need to show any food to them. Okay, so just check that out. So same thing here. The model is not told what is a good alloy, what is a good creditor. Model will basically give money to everyone, okay, and then check what type of people are giving back the money or not. Okay, so reinforcement learning may not work in this particular problem, but this is good for something like playing chess, playing game of Go. Okay, because the model can keep on continuously playing chess, and later it will realize whether this move resulted in me losing the game or not. Okay, and the good things with algorithms is they will continuously play millions or billions of games with each other, with itself. So there is something called AlphaGo. You may want to check it out. So AlphaGo was trained by playing games with another version of AlphaGo. Okay, so by itself they were playing games. Two models are playing games with each other, and both of them are continuously learning that what type of moves result in winning the game or losing the game. Okay, why reinforcement learning is considered to be better than the other two, supervised and unsupervised, given what I've said so far? See, we are not even giving data. It is playing with the environment and generating data actually. Okay. No, it's not brute force. Brute force would be wherein I check all alloys, like a grid I make and then just check everything. This is not brute force. It will decide that this is a better thing to check rather than something else. So, I'm going into parenting, but I can tell my son, okay, don't hit your head with the ball, right? It will hurt you. Okay. I should come up with a better example. The problem is that whenever labels are given to the model, we assume that the labels are correct, right? The labels are the best thing. So I think chess is a better example. Say I want to teach someone a chess, right? I'll be telling the person or the model that these are the right moves that you should do, and this will let you win the game. But what if I also have a limitation, right? My playing capacity also has a limitation. So whatever labels I'm giving, whatever moves I'm suggesting, they itself are not the best moves. Okay. So supervised learning has issues that the teacher or the person providing the labels itself is your bias, itself is your restriction, constraint, right? But in reinforcement, the model will play by itself and explore much more beyond than the teacher or the laborer itself knows. Okay, so only if you go through this reinforcement learning route, the model will be able to explore those moves that even the humans have not tested so far. Okay, so just by playing with the environment and just checking, exploring more, these models are able to go even beyond the human capability, and that's why you will see a lot of these models for a lot of Atari games, they do better than humans, lot of chess, Go, all these games, the reinforcement learning models do much better than what humans do. Okay, that is where humans are also losing into the competition. And in fact, a lot of the chess players now, they learn the moves from these games, from these models. They check what these models are doing, and then they have a team, like you may want to check it out. They have a team to just suggest them what are the moves that they should make, and then a lot of things happen in chess also. So reinforcement learning allows you to go even beyond the capability of the teacher or the labeler. Okay, that's why it can result in models which are better than human capabilities. Okay. it is, there's nothing, I mean, in this in a game of chess, there's not, you cannot define correctly in a very easy manner. What is the correct chess move? Right? There is a board position. Now, what is the correct chess move? So, one way you can define it is your probability of winning if you are able to compute it, your probability of winning if you are able to define it. That's how you can define it. Okay. But again, the point will come if the model is just trained on labeled data, meaning say you take all chess games played so far and all the moves made in those games. Using that only you try to train. Versus you go with a model which is based on reinforcement learning, you will see that the reinforcement learning model will do better. Why? Because not all moves of chess have been tested so far. They have not been played so far, right? Because the moves are so much higher in number. Okay. So model is coming up with its own strategy of playing the game. Yeah, so that's where the other important point is. You will see in material science there are very less cases of reinforcement learning, because in reinforcement learning lot of data training is needed. Okay. Yeah, so a huge amount of data generation, playing with the environment is needed for reinforcement learning to really blossom, and that is why you will see in material science we mostly have lot of examples of supervised learning and a few examples of unsupervised learning. Does that answer the question?
Yeah. Can you give me some example of unsupervised learning in material science?
I mean, there are actually, we have something in this coming slides. Yeah. Okay, so now let's understand it with some a little bit more example. So herein I am given on x-axis some size, on y-axis mass, and then some colors are given. And what I want to ask is, what do you think should be the color of this point, and this point? Okay. So this is the question. So what do you think is the color of this point? This one? Yeah. Okay. So this is green. What about this one? Red. This one? Okay. Okay. How many of you say orange? How many of you say blue? Okay. Someone for blue also. Okay, good. So, how did you guys decide? Yeah, nearest neighborhood, right? Something like this. So, what has unconsciously happened in your mind is that you drew a line, you imagined a line something like this. Any point lying beyond this line, you will label it as red. Any point lying above this line, you will label it as green. Okay. So this line, and then similarly in this case, this is red, this is this one. Now, depending on how you imagine the line, right? All of us are consciously or unconsciously imagining this line. You can draw this line like this way, and then you will say yellow or orange. Some of you may draw the line like this way, and they can still say it to be blue. Okay, that's why we heard some blue. And invariably, whenever I show this slide, there are always some people with blue. Majority is always with orange, but there are always some people with blue also. Okay, which means that all of us are imagining this line in our own way. Okay. Now, what is this line? In the context of all the slides so far, what is this line? This is our model. Okay. So this is my function. What is my x? Input to the model has to be x values. What is my x? Size and mass both. Okay. So this is something like my x1, this is my x2. Okay. So the coordinates are my x1, x2, and so this is how the model will look like. My model is this line, this function line, which consists of both x1, x2, and output is giving a prediction. So prediction can be +1 or -1. I mean, prediction is of the odd, something like green or red or things like that, whether something is above the line or below the line. Okay. So right now we all have imagined a line, and that's how we are making this thing. So any guesses on what this data is? Yeah. How do we know how to get the line? Okay, that's where the mathematics will come. What is the equation of best line? Okay, that's how you need to do. So just to okay, I'll answer it a little bit later. Okay, it's not that difficult. You can take distances from all the points and then optimize the equation of a line that minimizes your error. That's how you will get it. Okay, you got it? Okay. Okay, so any guesses on what this data is about? So body mass index, mass and size. Okay, height would have been better in that case, right? Yeah, no. Atoms. Okay, you are really into your PhD. Okay, so this is nothing but coins. Okay, so this way you can differentiate between, I think this data may be from US dollars, but you can imagine 1 rupee coin, 5 rupee coin. So how you can differentiate between different coins in a vending machine so that you know what coin is it. Okay, and coins will basically, with use, they may reduce in mass, and so it will be a distribution, right? It will never be one particular value. Okay. So same thing, we'll make it unsupervised. Okay. So in the last problem, what was my labels? It was the color. Okay. Now unsupervised I want to do for this case. How would that look like? So it will actually look something like this. I have my data, I have my x1, x2. I somehow want to transform this x1, x2 into a new space so that one group becomes together, the other group becomes better, and there is better separation between different groups. Okay. And in this case, it's just a toy example. So say this group is this one, say this group becomes this one, and then this group could be this one, and this group could be any one of these other. So the main point being, I am able to separate between these two groups better. Okay. So this is your unsupervised learning. You already have a few features, but you want to transform into a new space. So that's why these dimensions are a little bit arbitrary, right? What they exactly are. And basically I have a function. Again, for unsupervised also you are learning a function. But the output, instead of being a prediction or a label, is a new transformed feature. Okay, new transformed fingerprint. And this new transformed fingerprint is better at separating my data as compared to what I started with. Okay.
How do you know whether it is separated properly or not?
Yeah, again you will have some error metrics. Okay, we'll define some metrics through which we will define it. Okay. If you don't transform, then how will data change its location, right? So for example, this dimension 1 could be size times mass. It's a cumulative, okay, or something like size raised to power n, mass raised to the power n, m and n, like different powers. So it's a combination of this. It can be even more advanced, cos of size. Okay, so all types of functions you can think of.
How this
How? How is it giving? See, any function you do, you develop a mapping, right? It will give an output. Yeah. So say I take this point. I will enter its corresponding size and its corresponding mass into the function, and this point, I say it gets transformed into now this new dimension 1 and dimension 2. Okay, and it need not be just 2 dimensions. I can have even more dimensions or less dimension. So all these possibilities are there depending on how I do this thing. The main point being, now in this new space, the data is more separable, meaning the data is separate. So just observe these two groups, right? They are much more separated in this new space. Okay, so now let me give you some good examples of how people have used machine learning for actual materials discovery. So you will read this word a lot: acceleration of materials discovery using machine learning, right? So what does that mean? What you're seeing here is an example in the space of energy, like batteries, energy storage. So we know that batteries have safety issues because of fire. There is a lot of push for solid state batteries, all solid state batteries, wherein the electrolyte is also in solid form. Lot of inorganic materials are being looked for, which could be used as a replacement for ionic electrolytes that we have so far, right? The liquid electrolytes that we have. But the thing and the reason is because these solid state electrolytes have they don't easily burn or combust. Okay, but the problem with the solid state electrolytes is that lithium ion conductivity is very low. Okay, so what these guys were able to do was whatever you see in the open, non-solid open symbols, this is their historical data or training data, and whatever you see in the solid symbols is the new materials that they have discovered. Okay, and what you will see is a lot of solid symbols are much better in lithium ion conductivity as compared to the historical or the previous experimental data. Okay, so this is telling you how quickly they were able to identify new materials, solid state materials, which have high lithium ion conductivity. Okay, so this is one way of saying that, okay, rather than trying everything in my lab, just checking whether this thing has high lithium ion conductivity or not, okay, you can directly do this machine learning model to identify what materials have high lithium ion conductivity and simply go and do experiments on them. Okay. Any questions? Okay. So that's why these ML methods are a great tool to do. I mean, there are a lot of cases. I'm just showing one. Same thing for alloys, shape memory alloys, there are studies there. Same thing for polymers. Like whatever domain you talk about, people are now starting to use machine learning methods to just screen which are the candidates I should do my experiment on. And what I mean by experiment is not just literally your experiment in the lab. We know that DFT calculations are also very expensive. So what should be my next DFT calculation? That also machine learning model will tell. Okay. So whatever thing takes time, let me do machine learning model first. Let me screen out a few candidates and I'll only focus on the ML selected candidates. Okay, and that is why we are saying that it's accelerating materials discovery. So this is another example which is on polymer discovery. So herein notice we are looking at two properties. So we are going for polymers with high band gap as well as high glass transition temperature. And then the idea was, can we find new polymers which satisfy both these properties simultaneously? Okay, so without going into details, I mean each dot here is a new possible polymer candidate, and the ones which lie in this upper right triangle are being shown here. And see how, I think millions of polymers candidate were actually being predicted based on the model. Model predictions were made on millions of candidates, and these are some of the top cases that were identified based on machine learning method. Once you have identified, you can actually go ahead and do the DFT calculations on them or experiment on them to know what is their real value. what is their actual value, not the predicted value, but the actual value, which was also done in this case for the band gap, and they checked whether the band gap are really high or not. Okay. Yeah. So, I mean, now enough things are there to confirm that these models genuinely work. So this one is another interesting example. Let's see if I am able to play it. How can I do? Okay, I think this. Okay, so now you learned few examples where model is able to tell what materials are good for testing, right? Model is able to tell go for these materials. It has screened it for you. Once the model has screened that for you, you can attach a robotic platform to this machine learning model to make everything completely autonomous. Okay, so what you're seeing here, hopefully it runs, yeah. So what you're seeing here is a robotic arm which is being told by the model that go and make the polymer films in this manner. The arm will now knows that, okay, I need to use this as coating speed, this should be my solvent concentration, this should be my treatments, coating temperature, and so on. So the arm will basically, the robotic arm will make your polymer film. Not just it will make it, it will actually measure the electrical conductivity, optical measurement, these things will happen. And this new data that is become available to us will be given back to the model. The model, new iteration of model will happen, and that new model will again tell the robot, now do this experiment. Okay. So there is actually no human in the loop, and this thing is called a completely self-driven lab. Okay. So like in this case, let's go here. These are all the solvents. This is the place where the coating happens. This is the place where optical measurement is happening, and this is where the electrical measurement is happening. Okay. So robot is doing the experiment, model is telling what experiment to be done. They're just talking to each other, and then at the end of the day, in this case, in about 40 experiments, we were able to find that polymer film conditions, like processing conditions of polymer film, which result in a extremely good conductivity, electrical conductivity. Okay. If you look at the total number of experiments that were possible is of the order of millions. Okay. So, I mean, the two important things I want to highlight here is there is no human in the loop. Okay. Second important thing is, out of this entire space of 2 millions, you just did experiment on 50 or so cases, and still we were able to find good films which had the property that we needed. Okay. This is still not reinforcement learning, it is still supervised learning, but added layer of top of Bayesian optimization on it. It is still not reinforcement learning. Yeah. Yeah. Yeah, so I think in this case, first 10 experiments are fed in a slightly more clever way, not random. Then afterwards, it is the machine learning model doing it. Sorry? This one is in Argonne National Lab, so I am part of this work. So when I was there, that's when we did this thing. So it should be published soon. I mean, I'm hoping in next 1 month it will be published. Yeah. Okay, so yeah, this is one more example. We'll quickly do this. So LLMs, right? ChatGPT we started. I think last example I have is also about ChatGPT. So the way we are using ChatGPT in our lab is we are trying to give all the papers, journal articles to ChatGPT and asking it to make a data set for us. Okay. So one most important thing, whatever I talk so far, we always start with data, right? The data was already available, then I'm starting to build my model and then do more things with it. Lot of data that we have is available in the literature. It is not in that clean format as we want it to be. Okay. And that's where we are using ChatGPT to extract that data in a more cleaner format. So what you're seeing here is an actual abstract or paragraph from an article. And then I'm asking ChatGPT, can you tell me what alloys were made in this? What was the structure of these alloys, how they were synthesized, things like this. And then LLM will basically tell me, okay, this alloy was made, this was its structure, and these were the synthesis conditions. I can, the way you guys may be familiar with using ChatGPT is by entering in the browser, right? But there is an API available, just like how you were using Jarvis yesterday. Same way you can use OpenAI ChatGPT also. And because we have that API available, I can actually instead create a code which loops over paragraphs of different articles, and the ChatGPT queries are given, and for each paper it will tell me, okay, these alloys were there, these were the synthesis conditions, things like this, and I will quickly get a database. Okay, so these are the things available there. So I mean, it looks very good in this slide, but there are challenges in regards to the accuracy of the extraction. Okay, so that is something we are dealing in our group in this scenario. But this is another example how you can use these machine learning models for creating even a data set. Okay, any questions so far? Okay, this one, yeah. So you have to, so that is a tricky thing. You need to be able to provide this data meaning these paragraphs. So, I mean, you have to download, I mean, it should be available to you in some format as a text. Yeah. So the good thing is Elsevier and then some other journals, they have their own API, wherein rather than getting the publication journal article as a PDF, right? Generally we see it as a PDF, but in their backend it is stored as a XML file. So you can directly get an XML file if that journal article that publisher allows, and through that also you can. So that's how we are doing it. And there is a good community that is coming up to go through this method. Okay, a few papers, I mean, I would say maybe about 10 to 15 papers have been published in this area. Okay, any other question? So far we have gone through 10,000. So rather than asking my students to go through it and then extracting it, it's better to ask them to make a ChatGPT pipeline to do it. Same as rather than asking students to do experiment in the lab, you can ask them to work on robots who will do experiments for them. Okay.
In unsupervised learning, you said the data labels are not mentioned.
Yes.
So, let's say if we are performing an unsupervised learning, what are we expecting from that model?
Yeah, so right now I do not have a very good slide to explain that to you. At a very basic level, you want them to group them separately. Okay. Now imagine it like this. Let's see if I am able to explain. Actually, this paper, I recommend you to read this. They actually use unsupervised learning to do this thing. Okay. But let me try and explain it from this case. Okay. Say I do not have labels for this, okay, and then I grouped them. I grouped my materials in some way. For few of those, and then after grouping, it comes out to be like this. For few of those, say for 2 or 3 of these, I actually know the label. Say I know the label. and then these are say materials which are very high hardness. Now if I know that these have high hardness and they have been grouped together by a model to be in the same situation, there is a good chance that all of this group have high hardness. Okay. So now only from, see, yeah, this dimension 1, dimension 2 comes from the model. So model somehow identified that these things are together. While developing the model, I did not give the information these are good alloys. Okay. The model was only given that these are some alloys. You now group them. Now it so happens that I looked and checked that this group has 2 or 3 cases which are good, which means there is a good chance that the other people are also good. Okay, other candidates are also good. And this is some other way that people are trying to come up with new materials and do that. One more addition here is that the more data you have, the learning will be better. So the unsupervised grouping is actually always better than how a supervised learning model will be. The embedding or the, I mean, I'm using few words, the embeddings or the vectors that an unsupervised learning model learns is better than that of a supervised learning model. So there is also something called semi-supervised learning model, wherein you combine your unsupervised learning and supervised learning together, wherein the idea is that unsupervised learning will learn a better embedding space, better feature space, and the supervised learning model will do the job of telling you whether this is a good group or a bad group, things like that. Okay. Okay, so moving ahead. So these are conceptually this part is okay. We have a historical data, we need to fingerprint it, now develop a model. So practically how you do it, okay? Practically this is how you will do it. You will first collect data, then you will come up with a featureization technique. So you will find a way to fingerprint your materials, numerically represent them, train the model. Once the model training is done, then you will try to make predictions using that. So making predictions is something equivalent to you make predictions and then screen the materials which are giving good predictions. Okay. So let's, Kamal will cover more detailed machine learning models tomorrow. Today I'll just do very simple, one of the basic one, the linear regression model. Okay, very basic. He will cover a lot more tomorrow. Okay. So we'll start with this. This is a supervised learning linear regression model. So this is how the data is given to you. So first step was collect data. Okay. So this is how the data after collection looks like. And in this case, the second thing was featureize your thing. In this case, the feature is also given to me, which is X. Okay. I have only one feature, so it's a one-dimensional problem wherein I only have X values and then Y is something I want to predict. Okay. The question I want to pose to you is, say I have this new point X. Okay. There is a new alloy X or new polymer which is this point here or this point here. Now tell me what is the label it will have or what is the value it will have. So what do you think would be the value of this case? So somewhere around here, right? Okay, let me actually move to, so somewhere around here. What about this new point? So somewhere around here. Okay. Again, what we are doing? We are thinking of a line, okay, going here, and that line is our model. And when I'm given X, line basically means an equation, right? What type of equation will that be? Yeah, so they did this thing and then it will be equation of this type. Y is equals to mx plus c. In a more little bit tilting you towards the ML way of writing it, you will write it as W0 plus W1x. X is your feature and W0 and W1 are your weights. for a line, W0 is your intercept and W1 is your slope. Okay. So now this is how my model looks like. This is what we are doing. Now W0 and W1, W0, W1, these are known or unknown? These are unknown. If I change my W0, W1, say I change my W1. So basically I am talking about I am changing the slope while keeping the intercept same. Okay. If I am changing both W0 and W1, basically I am talking about different lines passing through this data. Okay. So this red line is something which looks like a best fit line. And say I draw one more line here. Let's see if I can do it. So say I draw one more line like this. This line will also have its corresponding W0 and W1. Is it a good fit or a bad fit? It's a bad fit. Now I need to define my good fit and bad fit, right? We know that this is bad fit, but what do I actually mean? So how will I define my good fit or bad fit? Error. Okay. I need to define my error, and once I define my error, that's when I will know what is my solution to this W0, W1. Okay. So what I'll do is, I'll also, okay, for now it's okay, X. Okay. So I always put a cap in front to tell me this is a machine learning model prediction, okay, Y cap, and that is given by W0, W1X. Okay. So what is my error? For all my blue points, for all my blue points, I know my Y cap is the prediction. For any given value of W0, W1, I know my Y cap, and Y minus Y cap will be the error. Okay. But I need to do it for all i's. I's are going on different blue points. Okay. So my error for a particular data point, for a particular blue point, will be given by this. Okay. Now I'll define something as mean square error. Okay. So what will that be? I take my yi minus y cap I square it. So square is done. Summation 1 by n. Summation will go from I equals to 1 to n. Okay. So I have taken a mean of my squared errors. So this is my mean square error. Okay. This is also, in some parlance, we can also call it as my cost function, loss function. Okay. These are generally denoted by letter J. Okay. Now what I need to do is, in all of this, what are the variables? Y is known. Okay. Yi's are known to me, because true for all the blue points, I know my yi's. Within this y cap I, xi's are also known to me. The only things which are unknown are W0 and W1. So what I need to do is, I need to differentiate my cost function J. Basically, I need to find that W0 and W1 which minimizes my J, which minimizes the error. How will you minimize a function? You basically differentiate it and then make it equal to 0. Okay. But in this case, I have two variables, W0 and W1. So basically, I need to do del J by del W0 equals to 0 and del J by del W1 equals to 0. And the good way to write a vectorial differential would be, you take this differential of J with respect to W1 and W0 and make it equals to 0. Okay. So this is a system of equations. It's not just one equation. It has two equations right now, del J by del W0 equals to 0 and del J by del W1 equals to 0. Okay. When you do this, we'll get value of W0 and W1 which will best fit my this thing. Okay, but let me do one thing, which is instead of just one dimension, say my thing was m dimension. Okay, I cannot plot it, but imagine I have data given to me in a m dimensional space, and from that data I am passing a something like a line I cannot pass. So what I'll be passing is a plane. Okay, and because now I'm talking about a plane in higher dimensions, it will be a hyperplane. Okay, what will be the equation of that hyperplane? Equation will be actually very similar. Okay, so it is still a linear equation, and instead of just w1 x1 like this one, I now have until xm. Okay, same I will differentiate my cost function, but now I need to write w0, w1 up till wm. So basically I have m equations, m differential equations, all of them equal to 0. And if you solve this, there are different ways by which you can solve it. We can also use linear algebra to solve it. And when you solve it, this is the solution that you will get, which is your x transpose x w cap equals to x transpose y. So what is my x here? So it's a x matrix transpose x matrix w cap. W cap is my weight vector. So what is weight vector? And this thing is a vector. Okay, so this is a matrix w cap vector x transpose matrix y vector. Okay, what is my y vector? My all n points. Okay, and how does the x matrix looks like? So this is my first data point x1, and this is my x1. So notice this one is data point 1, data point 2, data point n, and this one is feature 1 of my this is feature 1. This is my x2, and this whole thing goes up till xm. Okay, so this whole thing is your x matrix, and similarly your y is nothing but your y1, y2 up till yn. Yeah, very good. So W does have one extra dimension, which you will be able to accommodate here. So we can talk more. I'll explain you. Basically, you also have something called one more extra x naught. Okay, and the value of x naught is basically 1. Okay. So important point here being, this is your x, and x is known quantity because you know your blue points x values. Okay, w cap is what you want to find. You want to find that weights. X transpose is same. Y vector also you know, because y vectors are nothing but the values associated with these blue points. Okay, so if you solve this matrix equation, that's how you can get your w cap. Okay, same thing you can do if you really want to work hard. You can differentiate all those equations and then get it. That way also you can get it. Okay, Okay. So with this, let me quickly just mention. So this is how you can pictorially imagine, right? What does error mean? For any given value of W0 and W1, you have the red line, and associated with each blue point, you have an error. Okay. It is not necessary that always you have to take mean square error. There are other error metrics, other loss functions also that can be covered. But if you assume your model to be linear and you assume your error metric to be mean square error, this is how the result will look like. There are some other error metrics that people generally use. So one of them is coefficient of determination. Okay, I'll not talk too much about it, but just to give you an idea, the closer this value is to 1 means that it's a good model, and closer, I mean the value is equal to 0, which means it's a really poor model. Okay, so it ranges between 0 to 1, and yeah. Okay. So with this, we are ready for some hands-on session. So we'll quickly go through this, and then so you can either scan it, or then I think Google Drive link was available to you guys. So go ahead and then start pulling this up in your Google Drive. So the equation that we derived, we will basically make the model using that equation. Yeah. So until here it's okay? Okay. So now once you try to solve this thing, this is how the solution would look like. Okay. So remember, what are we trying to solve? W vector, basically W0, W1. All the X things and Y things are known to me. And because it's a these are M equations, I can use linear algebra to solve it, and this is how the solution will actually look like. In this solution, X now has become a matrix, and this is how my matrix looks like. Okay. So these are my different data points. So basically all my different blue points. But remember, I am talking about an example where the blue points are residing in a m-dimensional space. So for just one data point, I will have associated m values of X. So those m values are x1, x2 until xm. So this is my first data point, second blue point until n blue points, and this is how an X matrix looks like. Okay. So are people able to go and open up? Anyone facing issues with opening up the tutorial thing? So, yeah.
If we use that coefficient of determination, the cost function and the way of minimizing equations will be different.
Yeah. But no one uses coefficient of determination as a cost function. People generally don't use it. People will use something else, right? Like mean absolute error they may use. They may also use error of the order of 4. Okay. So there are different cost functions that people can. Sorry?
RMSE do people use?
Yeah, more RMSE is mean square error and RMSE in terms of cost function, they come out to be same only, and usually people use RMS, mean square error.
RMSE also this equation boils down to this.
Yeah. Okay. So, okay. So hopefully people are able to come here, and then you can go ahead. Kamal already talked about the Google notebooks, how we can work with them. So in this case, we'll be working on a high entropy alloy problem, wherein we'll try to build a model which has a high hardness, I mean, we want to build a model to predict alloy hardness. Okay. Okay, and then the data is taken from this paper, so that is also available. And what I'm doing is I'm simply using shift enter. So I hope people know shift enter we can use to run the cell. So I'm using shift enter to run my commands. In this case, the libraries that we are using, pandas library, Kamal already talked about yesterday. So whenever you have a table and you want to play with the table, that's why we are using pandas. There is a matplotlib library, mostly for plotting purposes. We'll also come across, we have also this scikit-learn library, which is a library that is a collection of different models. Okay, so we just want linear regression for now, but say tomorrow you are making a random forest model or some other different types of machine learning model. So this library allows you to make these models in a very easy fashion. Okay, so you will see it in a little bit also. So I went ahead and then basically loaded my data set. This is how the data set looks like. I have aluminum, cobalt, chromium, copper, iron, nickel. So these are my alloys, their composition. This is just some ID, not relevant. And this one is their Vickers hardness that has been experimentally measured. Okay. So anyone not familiar with alloys? Everyone is sort of familiar. Okay. So alloy is basically a random mixture of different elements, okay, a solid mixture, and in this case what is given is how much different element compositions are involved in that mixture. Okay. So example, in the first case it's a cobalt 25 atomic weight fraction, chromium 25 atomic weight fraction, iron and nickel also 25 atomic fraction, okay, each. And overall we have 120 alloys, and then I think 6, right? 1, 2, 3, 4, 5, 6. So 6 elements are possible in this data sets. And then if you want to do, like, if you can see it right here, right? I have my X separate and Y separate. Okay. So that's why the first thing I'm doing is actually doing a separation between my X matrix versus the Y column. And then I'm just looking if the things are looking okay or not. And then Kamal also discussed this. The first thing you want to do is you just want to simply visualize your data set. Okay. So I'm just visualizing what is the range of my hardness property, aluminum, cobalt, chromium, what are the range of their atomic fractions, how much are they present. Okay. And then what do you guys think, why it is important to visualize it? I think Kamal also mentioned it yesterday. What you're seeing is that there is some set of alloys which are giving low hardness and some set of alloys which are giving high hardness. You can also think it this manner that sometimes we need materials which are soft, sometimes we need materials which are hard. Okay. So in applications terms, both type of alloys may be actually useful. Okay. And we all love Gaussian, statisticians especially love Gaussian, but sometimes the data set does not follow it, and we should have good justification on why we want to remove anything. Okay. Although your point is valid, like say I know that my distribution should be Gaussian, but I do not see it to be Gaussian, then I can think of eliminating few things. But you should always have a logical reasoning behind why do you expect it to be Gaussian. Okay. So, but the point remains correct that by visualization you can get a good idea how does my data look like. You have some idea that the average will be somewhere around say 400 something. Okay. So this is the baseline model, right? So for around 400 is sort of my baseline model. If I see an alloy with a negative hardness, that should not be there. That triggers that, okay, something is wrong there. These things also make sense. Your atomic fraction should be between 0 and 1. Okay, so just quick idea about how does the data set looks like, just to see if nothing wrong is happening. Okay.
Can you talk a little bit more about the baseline model?
The baseline model, we have it. You will see coming up also. So now we'll go ahead and train the model. Before doing that, I have just created a function for plotting a plot. For just making a standardized parity plot. So I think Kamal also discussed yesterday, we make a parity plot wherein you can have, say, ground truth, your correct true y values on one axis and your y cap or machine learning values, prediction values on the other axis, and then you check whether they match or not. Okay. So because we'll be making multiple of these parity plots, I just made a function so that I can repeat the code again and again. I mean, I don't have to repeat the code again and again. And then the next thing, this is actually the same equation that I've written on the board. Okay. What I need to do is, I need to do x transpose x. Okay. Then I need to do x transpose y, which is on the right side. And then whatever I did, my x transpose x, I need to take its inverse. So that's where the inverse is also there. So basically the equation will become x transpose x inverse x transpose y. And this is exactly what I have calculated here. And then once I've calculated it, I know my W cap. Okay, then W cap becomes known. There are a few things I am skipping here, but this is how the solution will be. Okay, and then this is my W cap, which is the best model that is fitting my data. Okay, once I have my W cap, I can actually do this thing, x times x dot product of W cap. So imagine your x and you are taking dot product with W vector. So what will that give you? This multiplied by this vector. So that is my y1. This multiplied by second vector, that is my y cap 1, y cap 2. Okay. So this thing is basically giving me prediction on for these different alloys. For these 120 alloys, now I am getting a prediction. Okay. Yeah, whenever, so for inversion of a matrix, I am using this np dot linear algebra library. Just np dot dot, yeah. Okay. And then these are my y caps. So this is my y versus my y cap, and I am asking it to make a parity plot, and this is how it looks like. Okay. So then what do you guys think? Is this a decent prediction or? Okay, good. So the model looks good. And then we can quantify how good it is. How do we quantify? I still can compute my, see, error is still there. It is not that I can fit a plane which perfectly passes through all my data points. Okay. So there is still an error, but what I have found is the best hyperplane that is passing through my data. And for that best plane, what is the RMSE? Basically mean square error you take, and then you take under root of that, square root of that, and that is your 80. And then the R2 score, which I told you 1 is a good value, 0 is a bad value, that R2 score is around 0.81. Okay. So given that my range of alloy hardness is of the order of 100 to 800, right, around 800, I'm making an error of the order of 10%. My error is around 80. Okay. So from that perspective, it does look like to be a decent model. Okay. So in material science, generally speaking, R2 score of 0.7, 0.8, 0.9, even 1, depending on the problem, these are good ranges that you are in. Okay. Some problems are very much difficult. Even 0.7 is the best model that you have for that data set. Okay. This is slightly different from a CS community where you will see, okay, 0.99, 0.95, 0.98. Where am I applying gradient? Gradient descent. So I need not apply this. The solution to this is this. If you apply this, this is the solution you will get. Okay, but then, okay, now one more thing I can do is, I told you guys that, see, this is one manual way of doing it, right? We are writing the code ourselves. But for more sophisticated machine learning models that you will start seeing from today onwards, you need not write all the code by yourself, okay? Let alone understanding all the equations behind it, okay? So this is the simplest. So believe me, this is the simplest possible model that we can talk about, okay? So that's where you have the scikit-learn package. So sklearn package, you can directly, this is how you can build a linear regression model. So in there you call the linear regression thing, and then you just do something called linear regression dot fit, and you give your x and y. It will basically do the same thing. And then what I'm doing, and once it builds the model, you do model dot predict, and it will give you the predictions on this data set. Okay. What I'm trying to show is whether you solve the equations by yourself or you use the scikit-learn model, you are doing the same thing. Okay. In one case, you are writing the code yourself. In the other case, someone else has written the code. They have built an easier library for you to use, and you are using that one. Okay. I go ahead and do one more thing where I am printing the weights. If you remember what are my important model points here, it is just the W cap, meaning the weight vectors. And if you check the weight coefficients from the scikit-learn model versus the equation-based model that we have made, they are exactly the same. So it is telling you exactly same equations are being solved to make that library is also doing the same thing. Okay. And then there is this question about the baseline model. Okay. So one suggestion is, let's just make average predictions for all my 120 alloys, right? If I do that, the root mean square error that you will get is 186, and R2 score will be actually 0. Okay. And your difference between R2 score from 0 to 0.8 is telling you the information that the model has learned. This difference between RMSE going from 186 to now 80 is telling you how much information the model has learned, how much better your model is doing as compared to the baseline average model. Okay. Okay. So second point we have already covered, but then the third question is important. So which is, do you think there is any issue with the way we have computed accuracy of our linear regression model? Okay, overfitting might be there, but generally speaking, this is a simpler model, so you would not expect it to overfit. Actually, overfitting may also not be there. Actually, overfitting may not be there because you can, because of, you can always find an inverse linear transformation which will not result in overfitting. So, it is not about overfitting.
I mean, here we are simply using L2 norm, but using L1 norm.
No, I didn't use any norm.
But this resembles uses of L2 norm, right?
So LT norm, you are talking about the weight vector L2 norm, right? But there is no, see in my J,
I'm not talking about regularization. Like in general, like we can use lasso construct, right? Like this one.
that is all about the weight vector. Yeah. If I add some term here, that's where lasso and then that things regularization will come. My question is this, let me repeat my question. So the way we have talked about accuracy of my model, there is something wrong there. Okay, you're talking about randomization of data. What do you think? In this case, if I say I shuffle my rows, will it change the solution? So in this case, it will not change.
The whole data is being used for training. Whatever we have trained, the same thing we are trying to find
Yeah.
the error.
So this is a very important point, which is when I'm saying that my accuracy of the model is now say 0.81 R2 score, or I'm saying that now the new RMSE is 81. So that is incorrect because the same data points are used to determine my weight vector. And the same points I am saying to talk about accuracy of my model. So that is not allowed. Okay. You always should talk about accuracy of your model in the context of some new points. Okay. So I always explain this using like one example, which is say you guys are, you are part of a course. So during the course, I discuss some question and I tell you the answers for that question, for those questions. And then at the end of the course, I ask you the same questions and then I ask you to write answers for those. So obviously you will do better on those questions because same questions have been given answers to those during the class itself. Okay. What I should actually do is, whatever I taught in the course, I should ask questions on that subject, but slightly different questions which check your learning. Okay. In this case, what we are doing? We are showing some questions to the model. Same questions we are asking it for the answers and then saying that your accuracy is, your learning is like this. So that's not a good point, right? I need to ask some new data points, some new questions I need to ask to this model. Okay. And in order for us to do that, that's where the next concept comes in, which is cross-validation. Basically splitting your data into 2 or 3 components. One component is for training the model. Training the model means solving these equations, solving your cost function, getting your weight vector. Then there is another part of the data that you will use for testing your model. So basically just like how students have to give a test and at the end of a course, similarly new questions, new alloys will be shown to the model and I will ask, tell me about these questions, about these alloys, and then the performance on those alloys I will use for actually evaluating my model. Okay. So if we do this, there is another concept that has to come in. Which is cross-validation. Okay. So now, especially in material science, our data is always limited. Okay. If out of 120, I separate 50 alloys to just test my model, then I am only using around 70 alloys to train my model, which means that I'm not showing a model all the types of alloys data that could be possibly there. Okay. So making a bigger test set means you are sacrificing your training set. Training set is also needed to train the model. Okay. So now somehow I need to balance this. How can I have a good amount of training set as well and a good amount of testing set also? Okay. That's where cross-validation comes in. So what we will do is, we will basically divide our data set into different buckets. So for example, this is a 4-fold cross-validation example. So I'll divide my data set into 4 buckets. And first iteration, I will use one of the bucket to talk about accuracy of my model, and the remaining 3 buckets to train my model. Next iteration, I will use the first as well as the last 2 buckets to train my model, and the second bucket to test my model's accuracy. Third time, first 2 buckets are for training, the third bucket is for testing, the fourth bucket is for again for training. Okay, so this way I am looping over my entire data set. So every data point has one time become a training, it has at least become a test point, and other times it has become a training point. Okay, so by looping over my data set, I'm trying to balance between this, I'm using everything, but also not sacrificing a lot on my training and not sacrificing too much on my testing as well. Okay, that's how this balance is maintained. Okay. And this is exactly what we do next in this example. So basically, in this case, I'm using 5-fold cross validation. So each fold, 5 buckets are made, 4 buckets are used for training, and the 5th bucket is used for testing. Okay, so once you run this code, for every time you will get performance of the model on the training set as well as the testing set, and this is how the different performances look like. And this is how the final, you will now get 5 models with 5 different performances. Okay, so now what is a better estimate of my overall performance of the model? It is just the average of these 5 scenarios. Okay, so what I am showing here is the root mean square error of training, the R2 score of training, similarly root mean square error of test, and R2 score of test. So test here is also, you can call it validation. I mean, interchangeably sometimes the test and validation are used. And if I take an average of this, which looks like to be this, and this is a better estimate of my accuracy of the model as compared to the previous one. Okay, so look how the test error has also increased. Like now my test error is somewhere around 86 versus that of I think 81 that we were getting. So why do you think the test accuracy has increased? Yeah, see, models generally will have lower accuracy on, models generally will have lower error on training data, because same question you have used for training the model and same you are asking while evaluating the model, right? So same information has been used to determine the weight vector, and that is why you will see that training errors are in generally lesser as compared to that of your validation or test errors. Okay, and validation errors are a better estimate of your performance of the model as compared to your training error. In fact, like important point, whenever you are reading a paper, whenever you are looking at a work, whenever you are publishing your own work, please talk only about validation or test accuracies. Training accuracies have almost no meaning. There are a few things you can do with that, but in terms of accuracy, training accuracy has almost no meaning. Okay, only look at test accuracies.